Okay, so hi everybody, welcome back. Today in this video, we're going to be continuing on with our chapter 36 lecture on the theory of relativity. And where we left off last time was a discussion of relativistic velocity transformations. So we found a way to take a velocity as measured in one frame of reference and convert it to a velocity as measured in a different frame of reference. And we're doing this in a way that's compatible with the principles of relativity. So on that note, let's do another example. So we have Alice riding on a train, which is moving at a speed of 0.750 c relative to the ground. Bob is standing on the tracks directly in front of that oncoming train. Alice throws a baseball towards Bob, which moves at 0.950 c relative to her. What is the speed of the ball from Bob's perspective? And then as a follow-up, now let's consider the case where the train is moving away from Bob and Alice throws the ball towards him at the same speed. What would the speed of the ball be from Bob's perspective in that case? So pause the video, try to work this out using the relativistic velocity transformations that we derived in the last video and see what you come up with, then come back to the video and we'll go through it together. Okay, so let's start by defining some notation that we'll be using in this problem. Capital A represents Alice's frame of reference. Capital B represents Bob's frame of reference. And then lowercase b represents the baseball. Now we have to define a coordinate system that we're going to use to keep track of all the motion here. So how about we have the x-axis with the positive direction going to the right like this? So what are some velocities that we automatically know? The velocity of Alice relative to Bob. Well, she's moving at 0.75 c to the left in Bob's frame of reference. So we have VAB is minus 0.750 c. And then also, we know that VBA, that's the velocity of the baseball relative to Alice. She throws the baseball at 0.95 c, also going to the left, so it has a negative sign, negative 0.95 c. What we want to know is the velocity of the ball relative to Bob. We want to figure that out. How fast does Bob see the ball coming towards him? Now, if we were to do this using the Galilean transformations, so these are non-relativistic, well, what we would basically do is say the velocity of the ball relative to Bob equals the velocity of the ball relative to Alice plus the velocity of Alice relative to Bob. We'd simply be adding the two velocities. And what we'd get is negative 0.950 c minus 0.750 c, which would be negative 1.700 c. That would be faster than light. And as we know, that can't happen. Nothing can travel faster than the speed of light. So there's something wrong with that calculation, which is we need to be using the relativistic equations. So for relativistic transformations, we actually have V lowercase b uppercase b, that's the velocity of the ball relative to Bob, equals VBA, velocity of the ball relative to Alice, plus VAB. But then we have to divide that by 1 plus velocity of the ball relative to Alice times the velocity of Alice relative to Bob over c squared. That's the calculation we have to do to make this come out correctly. So here's what we have. We have negative 0.950 c minus 0.750 c on top On the bottom, we have 1 plus negative 0.950 C, negative 0.750 C over C squared. So the factors of C cancel on the bottom. We just have a pure number. And if you work this out, it comes out to minus 0.9927 C. And the negative sign just indicates we're moving to the left. So 0.993 C when we round it. Okay, so this does not have us traveling faster than light. Everything checks out here. Okay, there was a follow-up question, which was, if the train is moving away from Bob now, but then Alice still throws the ball to him, what we'll have is, okay, the velocity of Alice relative to Bob, she's not going to be moving to the left anymore. She's going to be moving to the right, away from him. So that will carry a positive sign, 0.750 C. But the velocity of the ball relative to Alice, since she's throwing it towards Bob, is still going to be carrying a negative sign and the same speed as before, 0.950 C. So if we want to find the velocity of the ball relative to Bob, it's actually the same calculation we did before. So let me just circle the equation. Still using that. But the inputs are different. We have negative 0.950 C for the velocity of the ball relative to Alice, and then plus 0.750 C for the velocity of Alice relative to Bob. Then divide that by 1 plus, those two velocities again are 0.950 C times 0.750 C over C squared. So the C's will cancel, as I was saying earlier. And this comes out to negative 0.6957 C, or negative 0.696 C. So again, the negative sign just means we're moving to the left. And of course, the ball is moving slower now because Alice is moving away from Bob as she throws it. So that's how this works out. And so as a follow-up to that, let's consider the same scenario where Alice is riding on a train, moving at a speed of 0.75 C relative to the ground. And then we have Bob standing on the tracks in front of the oncoming train. Now, instead of throwing a baseball, Alice is instead going to shine a flashlight towards Bob. The question here is, what is the speed of that light from Bob's perspective? So how fast is Bob going to see that light beam coming towards him? So use the same relativistic velocity equations that we used before, okay? And then after that, consider the case where the train is moving away from Bob and Alice shines the light towards him. In that case, what is the speed of light in Bob's frame of reference from his perspective? So pause the video, try to work these out, and then we'll go through it together. Okay, so again, we'll start with some notation. A, that's Alice's frame. B, capital B is Bob's frame. And then L is the light beam. Okay? So the same exact equation applies, except we're now applying it to the light beam. VLB, the velocity of that light beam relative to Bob, is what we want to know, is equal to VLA, the velocity of the light beam relative to Alice, plus VAB, the velocity of Alice relative to Bob, divided by 1 plus those same two velocities, VLA times VAB, multiplied together, over C squared. That's how we transform velocities in relativity. So what do we know? Well, just like before, VAB is negative 0.750 C, I'm defining the positive x direction to be to the right, so Alice is moving to the left. That's going to be a negative velocity. And then VLA, the velocity of that light beam relative to Alice, well, that would be just minus c. It's moving at the speed of light, but it's moving to the left, so it has a negative sign. Okay, so let's plug that into our equation here. VLA minus c. VAB is minus 0.750 c. We're dividing that by 1 plus VLA, that's again minus c, times VAB, that's minus 0.750 c. And we're dividing that by c squared. So here, what do we have on top? We have minus 1.750 c. So we have c and then minus 0.750 c, so add that together, you get minus 1.750 c. On the bottom, well, we have 1 plus 0.750, so 1.750 on the bottom, which gives you minus c. So same speed of light for both Alice and Bob. Remember, the whole basis of the theory of relativity rests on the fact that the speed of light is constant. Doesn't matter how fast the source of that light is moving towards you or away from you, you see the same exact speed. So that's reflected in our equations here. Okay, if the train is moving away, that's the follow-up question. If the train is moving away now, away from Bob, so now we'll have VAB is going to be positive 0.750 c, so we're just moving to the right now. VLA, velocity of the light beam relative to Alice. She's shining it towards Bob. She's directing it to the left, so we have minus c right here. And we'll use the same exact equation as before to calculate VLB. So we have VLA, that's minus c. We have VAB, that's plus 0.750 c. And we're dividing that by 1 plus minus c times 0.750 c over c squared. Okay, so on top, we have negative 1 plus 0.75, which works out to negative 0.25 times c. On the bottom, we have 1 minus 0.75, which is 0.25. So it's still the case that the light beam is going to the left at speed c. So these relativistic velocity transformations work out so that a light beam, no matter what frame of reference it's observed in, is moving at speed c. That's what we see here. So that brings us to Lorentz invariants. So this is something we're not going to dive super deep into, but I do want to give you some sense of it. If you study relativity after this class at the university level, you'll learn a lot about Lorentz invariants. And the motivation here is we've seen all sorts of things like length and time that we used to think were absolute, but actually are relative. Two different people in different frames of reference can disagree about how much time passes between two events. So it's natural to wonder whether anything is absolute. Is there any sort of quantity that everybody can agree on regardless of their frame of reference? Well, it turns out the answer is yes. This is what we would call a Lorentz invariant. So a Lorentz invariant is a quantity that is always measured to be the same value in every single frame of reference. A fancy way of saying that is it's invariant, it doesn't change under a Lorentz transformation. So there are many examples of Lorentz invariants in relativity. Mass is an example. So regardless of how you're moving, we can all agree on what the mass of an object is. Another example would be the speed of light. The speed of light is the same regardless of your frame of reference. And another example is called a space-time interval. This is a really interesting example. So the definition of the space-time interval, delta S, is the following. Delta S squared is equal to delta x squared plus delta y squared plus delta z squared, and then minus c times delta t squared. This is what defines a space-time interval. So all of these deltas refer to a difference in the space-time coordinates between two events. So if I have x1, y1, z1, and t1 as the first event, and then x2, y2, z2, t2 as my second event, delta x would be the distance on the x-axis between those two events, delta y would be the distance on the y-axis between the two events, and so on. So delta S, defined in this way, is a Lorentz invariant quantity, meaning regardless of your frame of reference, if there are two different events, we can all agree on what the space-time interval delta S is for those two events. So a little bit more about the space-time interval. I want to remind you how we calculate distance. If I have 2 points, and I know the x, y, and z coordinates of each point, the distance between them is given by the square root of x2 minus x1 squared. So just take the difference of the x coordinates and then square that. And then take that, add to it y2 minus y1 squared, and then z2 minus z1 squared. That's the distance formula. And, x2 minus x1, we could just call that delta x if we wanted to. y2 minus y1, we could call that delta y. And this could be delta z in a more compact notation. But the point is, this is not a Lorentz invariant. So different observers in different frames of reference are not necessarily going to agree on distance. And we already saw this. We learned about length contraction. The idea is different observers don't agree on the distance between 2 points or the length of an object, right? That's not Lorentz invariant. We also have time intervals. Okay, we can measure how much time passes between two events. And we can write this as T2 minus T1, or as a shorthand, delta T. That's also not Lorentz invariant. Okay, we already saw there's an effect called time dilation. Different observers in different frames of reference are going to measure different amounts of time that pass between two events. But if we combine these two things, distance and time interval, into an object that includes both, called our 4D space-time interval, well, then we have delta S equals the square root delta x squared plus delta y squared plus delta z squared, and then we have to subtract c times delta t squared. So I'm not going to prove this, but this is a Lorentz invariant. So all observers can agree on this quantity. So notice that this equation is similar to the Pythagorean theorem. So this is similar to the equation we use to calculate the hypotenuse of a right triangle. Okay? But it's in 4D space. So you can think about this as the four-dimensional version of the Pythagorean theorem, not in normal flat space, but in something called Minkowski space. Okay, so if you take a more advanced physics class where you continue to learn about relativity, you'll learn all about Minkowski space and how we do geometry in that 4D space. Okay, so that takes us to relativistic dynamics. So everything we've been doing up until this point can be called relativistic kinematics. So we're seeing how to describe motion in terms of position and time and velocity, things like this, in relativistic terms. But now what we're going to do is bring in things like momentum and energy into the picture and see what relativity has to say about those concepts. And as we do that, we're going to come across the famous equation E equals mc squared that you've probably seen before. We're actually going to see where that comes from and what it means. So let's get into it. So one thing that we need to be clear about is there are certain principles of physics like conservation of momentum and conservation of energy that we still want to hold true, even though we've redefined our notions of space and time. So if we want conservation of momentum, P initial equals P final to hold, even when particles are moving at relativistic speeds, like close to the speed of light, we actually have to modify our definition of momentum. So P, momentum, in classical physics is equal to m times v, just mass times velocity. The relativistic version of momentum is P equals gamma times mv. So we need this factor of gamma out front for conservation of momentum to still work at very large speeds. So this is the new definition of momentum in relativity. Okay, you may remember the work-energy theorem. You were taught this back in Physics 45. The work-energy theorem says that the total amount of work done on an object is equal to its change in kinetic energy. And again, we want that to hold true at relativistic speeds. So in order for that to work, Einstein figured out that we have to change the definition of kinetic energy. So instead of K equaling 1/2 mv squared, this is the new definition. K is equal to gamma minus 1 times m times c squared. That's relativistic kinetic energy. So I do want to point something out about these new definitions. In the non-relativistic limit, when v is much, much less than c, when we're moving a lot slower than the speed of light, these new definitions reduce down to the old formulas that you're used to from classical physics. So when things are moving slowly, not close to the speed of light, we have P equals m times v, and K equals 1/2 mv squared. So let's see how that works out. We'll start with relativistic momentum. Which is P equals gamma times mv. But in the non-relativistic limit, that means the speed is much, much less than c. We saw earlier that gamma will be very close to 1. So gamma is approximately just equal to 1 in that limit. And so the momentum will simply be approximately equal to m times v. So we get the classical definition of momentum in the non-relativistic limit. So that all works. For relativistic kinetic energy, here's what we have. So the definition is K is equal to gamma minus 1 times mc squared. So we want to be careful here. We don't want to just plug in gamma equals 1 and then end up with 0 for the kinetic energy. Okay, we want to say something a little bit more precise than that. So remember, the definition of gamma is this is 1 over the square root of 1 minus v squared over c squared. So how about we write this as 1 over the square root of 1 minus x squared, where we define x to be v over c, just for simplicity. So if we take this function, 1 over the square root of 1 minus x squared, and we do the Taylor series for that, do the Taylor series expansion, this works out to 1 plus x squared divided by 2 plus 3x to the fourth divided by 8. And there's some other terms, but let's just write the first three like this. That's the Taylor series expansion. So how about we put that into the formula for kinetic energy? So here, K is equal to gamma minus 1, but for gamma, we're going to use the Taylor series expansion. 1 plus x squared over 2 plus 3x to the fourth divided by 8. And then that sum actually goes on forever, but then we have a minus 1. And that multiplies mc squared. Well, in the non-relativistic limit, again, that means v is much, much less than c. Well, x, as we defined it over here, is v divided by c, so x is very small. It's much, much less than 1. And that means we'll only keep the first order term. So here's what I mean by that. This positive 1 right here cancels with this negative 1 right here. And then the first term is x squared over 2. The next one is 3x to the fourth over 8. And if we keep going, it's just higher and higher powers of x. But x is a really small number. So those really high powers of x are going to be very small, right? X to the fourth, x to the sixth, etc. are very small. So we'll ignore them. So as an approximation, we can say k is approximately equal to, we have x squared over 2, just keeping that first term, times mc squared. But remember, the definition of x is just v over c. So we have 1/2 times v over c squared times mc squared. So that's 1/2 times v squared over c squared times m times c squared. Cancel out the c's. And that gives us 1/2 mv squared. So once again, in the non-relativistic limit, this new definition of kinetic energy just reduces down to 1/2 mv squared, which is the familiar formula from classical physics. So let's get some practice making calculations of relativistic kinetic energy. So how much energy is required to accelerate a proton, which has a mass of 1.67 times 10 to the minus 27 kilograms, starting from rest to a speed of 0.900 c? Then, how much energy is required to accelerate a proton from 0.900 c to 0.999 c? And then, as a final question, how much energy would be required to accelerate the proton to the speed of light? So if we wanted to get it to the speed c, how much energy would that take? So we can accelerate particles like protons in particle accelerators. This is one example of such an accelerator. It's called the Tevatron. It's located at Fermilab in Illinois. So let's work this one out. We'll start with the work-energy theorem. So this says that the work done on an object is equal to its change in kinetic energy. So we're going to apply that to the proton. So delta K is just K final minus K initial. And for the kinetic energy, we have this new definition which I'll write down. We have gamma minus 1 times mc squared. So for K final, it's going to be gamma final minus 1 times mc squared. And then for K initial, we have gamma initial minus 1 times mc squared. Factor of 1 can cancel out. So that would be gamma final minus gamma initial times mc squared. And then let's just remember what gamma is. That's the square root, 1 over the square root of 1 minus v squared over c squared. So the work needed is going to be gamma final, which is 1 divided by the square root of 1 minus v final squared over c squared, minus 1 over the square root of 1 minus v initial squared over c squared, and then multiply that by mc squared. So that's the amount of work required to change the kinetic energy by a certain amount. Okay, so in the first question, we're going to go from v initial equals 0, we're going to start from rest, to v final is 0.900 C. And the work required to do that, we can now calculate. It's going to be, 1 over the square root of 1 minus v final squared over c squared. So that's going to be 0.900 squared. And then minus 1 over the square root of, 1 minus v initial squared is 1 minus 0, as we start from rest. So that's what we have. Okay, and that's multiplying mc squared. So the mass of the proton, 1.67, 10 to the minus 27 kilograms. C is the speed of light, 3.00, 10 to the 8 meters per second, and we're going to square that. Okay, so if you calculate this, you're going to get 1.945 times 10 to the minus 10. Keep 3 sig figs though. And the units here are kilograms, and then we have meters squared per second squared, but we should recognize that that unit is just a joule. So rounding it off to 3 sig figs, 1.95, 10 to the minus 10 joules. That's how much energy would be required to get the proton from 0 speed to 90% of the speed of light. All right, so what if we want to go from V initial is 90% of the speed of light, 0.900 C, to V final is 99.9% of the speed of light, so 0.999 C. Well, then the work would be, we have 1 over the square root of 1 minus V final squared over C squared, so that's going to be 0.999 squared, minus 1 over the square root of 1 minus V initial squared over C squared, that's going to be 0.900 squared. Okay, and then we multiply by the mass of the proton, 1.67, 10 to the minus 27 kilograms, times 3.00, 10 to the 8 meters per second squared, that's C squared. Okay, now that works out to 3.02, 10 to the minus 9 joules. So notice something that's happening here. This is a bigger amount of energy than this. So it takes more energy just to get that extra 10% or so of speed compared to the first 90%. So as we start to approach the speed of light, it gets harder and harder to accelerate this thing. Now, if we want to get to a final speed which is exactly equal to c, actually it doesn't matter what the starting speed is, for any v initial, here's what the work will be. You're going to have 1 over the square root of 1 minus v final squared over c squared, but if v final is exactly equal to c, then we're subtracting 1 right here. And then we subtract something here, it doesn't really matter what it is, times mc squared. But here, focus on this term. This is 1 over 0. That's going to approach infinity. So, as we approach the speed of light, the energy required to accelerate an object to that speed starts to approach infinity, which is another way of indicating, as we've seen before, that hitting the speed of light or exceeding the speed of light is not possible for any object. So here's one for you guys to try out. Let's consider an object moving at 5% of the speed of light. What is the percent error that you'll accumulate in a calculation of the object's momentum if you use the classical formula, which is an approximation, rather than the exact relativistic formula? So we have an object moving at 5% of the speed of light. How much error do we get if we use P equals mv, the classical formula, versus the relativistic P equals gamma times mv? So remember, percent error is approximate minus exact over the exact value times 100. So try to work this out, pause the video, and then come back to it when you have your answer. Okay, so if we're moving at 5% of light speed, that means v is equal to 0.05 c. Now, the exact formula for the momentum would be P equals gamma times mv. This is relativistic. The approximate momentum well, that would be the classical formula. P is just equal to mv. That's non-relativistic. So the percent error is going to be, again, the approximate value minus the exact value over the exact value, and then times 100. Okay. So this is mv minus gamma times mv divided by gamma times mv, and then times 100. So mv can just be canceled out across the board. So this would be 1 divided by gamma minus 1 times 100 after we simplify the expression. And remember, gamma is 1 over the square root of 1 minus v squared over c squared. So the error that we're looking at is the square root of 1 minus v squared over c squared, because that's 1 over gamma, minus 1 times 100. So in this case, we have the square root of 1 minus, we said v is 0.05 c, so v over c is 0.05, and we square that. And then we subtract 1, and then we multiply 100. What does that equal? Well, if you crunch these numbers, it's negative 0.125%. So even though we're moving at 5% of the speed of light, which is really fast, it's not really that much of an error. So the relativistic effects are still not really kicking in that much, but we're slightly underestimating the momentum by using, of course, the non-relativistic formula. That's what we're seeing here. So let's take a closer look now at relativistic energy. Kinetic energy, the energy associated with motion, is given by gamma minus 1 times mc squared, okay? So let's take that and let's distribute the mc squared into the parentheses. So we have k equals gamma times mc squared minus mc squared. So let's take that and rearrange the terms. Let's add mc squared to both sides. And what we have is gamma times mc squared is equal to k, the kinetic energy, plus mc squared. So how do we interpret this equation here? Well, the term on the left represents the total energy of a moving object. So let's call that E for total energy. And it consists of two parts. If we take the kinetic energy of the object and then we add it to mc squared, we get the total energy. So K, of course, is the kinetic energy. This last term here, mc squared, is what we call the rest energy. So let's think about that. The rest energy, which I'm labeling as E0 or E0, that's a type of energy that will be present even when the object is not moving. Notice how this term, mc squared, doesn't depend on the speed of the object. Okay? It just depends on the mass and the speed of light. So that is a type of energy that will be present even when the object is not moving. Even if the kinetic energy is 0, we'll still have this rest energy present. So the total energy of a moving object, as we said, is the sum of kinetic and the rest energy. But we can write this as gamma times mc squared. So the total energy E is equal to gamma times mc squared. Okay? So if we consider an object that is not moving, okay, gamma will approach 1 as the speed of the object approaches 0. So if the total energy of an object is given by gamma times mc squared, and we stipulate that the object is at rest, that means gamma is equal to 1. So then E is equal to mc squared. That's Einstein's famous equation. That's where it comes from. And what this is saying is that if the kinetic energy is 0, all of an object's energy is in the form of rest energy. So you'll get the total energy is just the rest energy, mc squared. That's what this is saying. Now, unless an object is moving really close to the speed of light, the total energy is mostly going to be this rest energy. This is going to be much bigger than the kinetic energy. Okay? And to really see how that works, let's do a few example calculations. Let's calculate the kinetic energy and the rest energy of a 125 kilogram linebacker running towards you at 6.75 meters per second. So we'll compare those two in this case. And then as a second example, calculate the kinetic energy and the rest energy of a proton with a mass of 1.67 10 to the minus 27 kilograms moving at 0.999 C. So let's work it out. Okay, so let's do the calculations for the linebacker, where the mass is 125 kilograms and the speed is 6.75 meters per second. So that would be typical of a football player running down a field. Okay? Now, the kinetic energy, we can just use the old formula 1/2 mv squared. This will work perfectly fine because v, the speed of the linebacker, is so much less than the speed of light. The classical formula will work. So let's use it. And so we have 1/2 times 125 kilograms times 6.75 meters per second squared. That would be the kinetic energy of this linebacker, which is 2,847 kilograms meters squared per second squared. We'll actually keep 3 sig figs on that. So the kinetic energy is about 2.85 10 to the 3 joules. So this is kinetic. Now, for the rest energy, that's given by E0, that's mc squared. So we take the mass of the linebacker, 125 kilograms, multiplied by c squared, 3.00, 10 to the 8 meters per second, and square that. And what this will come out to is 1.13 times 10 to the 19 joules. So what we can say is, this is our rest energy. The rest energy, E naught, is much, much bigger than the kinetic energy, K. So we are definitely in the non-relativistic regime here. Okay, now if we consider the proton, okay, now the mass is 1.67, 10 to the minus 27 kilograms, and the speed is 99.9% of the speed of light, 0.999 c. Okay, so for the kinetic energy, I'm not going to be able to use the classical physics formula because we're not in the low speed limit where v is a lot less than c. Instead, I have to use the relativistic formula, which is k is equal to gamma minus 1 times mc squared. So k is equal to gamma, which is 1 over the square root of 1 minus v squared over c squared, minus 1 times mc squared. Okay, so let's plug in what we know. We have 1 over the square root of 1 minus 0.999 squared, minus 1 times the mass, 1.67, 10 to the minus 27 kilograms, times c squared, which is 3.00, times 10 to the 8 meters per second squared. Okay, that works out to 3.21, 10 to the minus 9 joules. That's kinetic energy. Okay, now rest energy, E naught, that's just mc squared. So we have the mass, 1.67, 10 to the minus 27 kilograms, times 3 times 10 to the 8 meters per second, and we square that. And this gives us 1.50, 10 to the minus 10 joules for the rest energy. So in this case, the kinetic energy is actually much, much bigger than the rest energy. We're not in the non-relativistic regime. We're in what's called the hyper-relativistic regime here, because this proton is moving very, very close to the speed of light. So we've developed some formulas that describe relativistic energy. But now let's dig a little bit deeper into them to try to understand the underlying concepts behind these equations. So let's take it to the basics. What is energy? Well, in classical physics, energy is fundamentally a conserved quantity. So there are different forms that energy can take on, like kinetic energy, potential energy, internal energy, all this. But overall, in any process that happens, energy is going to be conserved. Now, another concept that we have from classical physics is mass. Now, in the framework of Newton's laws of motion, mass is an object's resistance to being accelerated. The more mass it has, the more resistant it is to being accelerated. And we can see that in the equation F equals ma. The more mass an object has, the greater the force you would need to apply to it to get it to accelerate. So that's what mass is in classical physics. Now in relativity, we have this idea of rest energy. So rest energy is the energy an object has even if it's not moving, even if it's just at rest. So we can think of the rest energy as the energy confined in the object, confined within the object. So Einstein's equation, E naught, the rest energy, is equal to mc squared, implies an equivalence between rest energy and mass. The rest energy and the mass are just related by a constant, c squared. So there's an equivalence between E naught and m, between the rest energy and the mass. So what Einstein realized is that mass must decrease whenever an object gives off energy. Because if the rest energy goes down because the object has given off some energy to the environment, that implies the mass has to go down. And on the other hand, if an object absorbs energy, if it takes energy in, then E naught increases. And that means the mass has to go up. So in Einstein's relativity, mass has a sort of different character than in old school Newtonian physics. So in Newton's framework, mass is a constant property of an object. An object's mass is not going to change unless you literally remove material from it or add material to it, but otherwise the mass is not going to change. In Einstein's framework, that's not the case. Mass can change if the rest energy of the object changes. So quite literally, if I heat something up, I increase its rest energy, I also increase its mass. If I cool something off, I decrease its rest energy and I decrease its mass. That's what this equation is really saying. Now, usually that effect, these changes in mass, are very, very small and in fact impossible to measure because they're so small. But in some instances, this is a very important effect, and in particular in nuclear reactions. So next, let's take a look at a couple examples that illustrate the mass-energy equivalence. So in this first example, we're going to consider a photon which is confined to a box which has negligible mass and perfectly reflective walls. So remember, a photon is just a particle of light, and light has no mass. So this photon itself doesn't have any mass. And we're going to assume, just for this example, that the box itself also doesn't have any mass. And the walls of the box are perfectly reflective, meaning the photon will just bounce around inside this box forever and it will never be absorbed by the walls of the box. So if we take a look at the individual parts of the system, the photon and the box itself, individually those don't have any mass. But when we consider them together as a system, where again the photon is bouncing around inside of the box, this system does have mass because it has energy. This photon has energy, we'll call that E naught. So the mass of this system would just be E naught divided by c squared. Okay? So even though the individual parts of the system have no mass, together as they interact, they do have mass. Another example, which is very similar to that, is the proton. So a proton is actually made out of 3 smaller particles, which are called quarks. And if we take the individual masses of the 3 quarks that make up a proton, and we add them together, the combined mass of those individual quarks is only about 1% of the mass of the proton. So that means most of the mass of the proton actually comes from the energy that these quarks have as they bounce around and interact with each other inside of the proton. So you can't actually just add up the mass of the individual parts of something to get the total mass of the combined system, okay? That's actually not how it works according to the mass-energy equivalence, because some of the mass of the proton, for example, in fact, most of the mass of the proton, 99% of it, comes from the energy of the quarks that are moving around inside of it. Let's talk a little bit about nuclear reactions. So a nuclear reaction is any process that causes the nucleus of an atom to transform into a different type of nucleus. And there are 2 basic types of nuclear reactions. So we have nuclear fission. Fission is when a large nucleus splits into 2 or more smaller nuclei. So radioactive elements like uranium are constantly undergoing nuclear fission. It's a random process that the nuclei undergo. So let's take a look down here at an example of a nuclear fission reaction. So first of all, when you see a nucleus, it's labeled by its chemical symbol. So this would be uranium. The U stands for uranium. The 92, that number on the bottom represents how many protons there are in that nucleus. And then the number 236 on top is the total number of protons and neutrons. So we have right here a uranium atom with 92 protons and 236 total protons and neutrons. So what can happen to this nucleus is it can split into barium-144, krypton-89, and then also it will let off 3 neutrons like this. This is a fission reaction because we have a larger nucleus splitting into smaller nuclei. Okay, that's fission. Now, fusion, on the other hand, is when we have 2 or more small nuclei that are smashed together to form a larger nucleus. So we're going in the other direction. So we're making a larger nucleus by fusing things together. So here's an example of a fusion reaction. So we have hydrogen 2. So that's a hydrogen atom with 1 proton and 1 neutron in the nucleus. And then we have hydrogen 3, which is 1 proton and 2 neutrons. These are just 2 different versions of hydrogen. And if we smash them together with enough energy, we can create helium-4. And then we also let off a neutron. But we've created a larger nucleus, a helium nucleus with 2 protons and 2 neutrons. That's an example of a fusion reaction. And actually, this is what's happening inside of the core of every star, fusion reactions. These reactions let off tons of energy, and that's what causes them to shine so brightly. It's the fusion reactions happening in the core. So let's do an example involving a nuclear fission reaction. So in one type of nuclear fission reaction, a uranium-232 atom with a mass of 232.03714 U. So this U represents an atomic mass unit. It decays into a helium-4 atom with a mass of 4.00260 U. And a thorium-228 atom with a mass of 228.02873 U. So again, U is the atomic mass unit. It's equal to 1.6605 times 10 to the minus 27 kilograms. Okay, so the question is, what is the energy in joules released when a single uranium-232 atom decays? And then as a follow-up, what is the energy released when a 1 kilogram sample of uranium-232 decays? So the reaction we're looking at is uranium-232 is what we start with. It decays into thorium-228 and helium-4, and then it also releases some energy. We're going to calculate how much energy is released. So we start off with a uranium-232 atom. This is the initial state. This atom undergoes fission, so it splits into a thorium-228 atom, as well as a helium-4 atom. And that's the final state. So we can calculate the change in rest energy between the initial state and the final state. That would be delta E0. So that's going to be E0 final minus E0 initial. And let's remember that rest energy is just given by mc squared. So we have m final times c squared minus m initial times c squared, which we can just factor the c out of this expression, and we have m final minus m initial times c squared, or in more compact terms, delta m, the overall change in mass, times c squared. So that's the idea. The total mass that we have in our system here changes between the initial state and the final state, and we can calculate that change. And that's going to lead to a change in the rest energy. Okay, so now let's calculate the total change in mass delta M. So delta M is equal to, okay, the final mass that we have is the combined mass of the helium-4 and the thorium-228. So for the thorium-228, the mass is 228.02873 atomic mass units. For the helium-4, it's 4.00260 atomic mass units. And then that's M final. We're subtracting now M initial, which is just the mass of the uranium-232. So that's 232.03714 atomic mass units. So if you actually calculate this, it comes out to minus 0.00581 atomic mass units. And what we can do next is convert that to kilograms, because in every 1 atomic mass unit, we have 1.6605 times 10 to the minus 27 kilograms. So now we're calculating the overall change in mass in one of these fission reactions in units of kilograms. And that's going to be minus 9.648 times 10 to the minus 30 kilograms. So here, we've lost some mass. The mass is not constant. We can actually lose mass. And as a result of that, we also have lost rest energy, delta E0, which again is delta M times C squared. So this is our delta M. If we multiply it by C squared, we get minus 9.648, keeping 3 sig figs now because we have 3 sig figs over here, times 10 to the minus 30 kilograms. C squared is 3.0010 to the 8 meters per second, and we square that. And this works out to minus 8.683 10 to the minus 13 joules. Okay, so here's the idea. 8.68 10 to the minus 13 joules of rest energy is lost in each reaction. So every time there's a fission reaction like this, this is the loss of energy. But since energy is conserved, the energy lost from the system goes out into the environment. So this energy is released into the environment. So typically that would just be in the form of heat, right? The particles are moving faster than before. Okay, so the next question is, if we have 1 kilogram of this uranium-232 that undergoes fission, how much energy will be released? Well, we know that 8.683 10 to the minus 13 joules are released for every atom. Okay, that's the amount of energy released when one of these atoms undergoes fission. But we know that in every 1 mole, we have 6.022 10 to the 23 atoms. So that's a conversion factor to go from atoms to moles. Now, here's another thing that you should remember from very early on in the semester. If we know the mass of an atom in atomic mass units, that's equivalent to the number of grams per mole of that substance. So uranium-232 has an atomic mass of 232.03714. So that's how many grams we have in every mole of that substance. So I have another conversion factor. We can cancel out moles, and now we have grams on the bottom. But what I really want is kilograms. So we have 1,000 grams on top for every 1 kilogram. So see what I just did? I converted from joules per atom, so how many joules of energy are released for every atom, to joules per kilogram. How much energy is released for every kilogram of material that undergoes fission. That's what we want to do. So this comes out to 2.253 10 to the 12 joules per kilogram, which we'd round to 2.25 10 to the 12 joules for every kilogram. Now, that's an insane amount of energy if you think about it, because a kilogram of material is not that much. You can easily hold that in the palm of your hand. But what we're saying here is, in that 1 kilogram of material, we're getting about 2 trillion joules worth of energy out of it, okay? Now, if we compare that to other sources of energy, like if we compare this to burning coal, as an example. When we burn coal, we only get about 10 to the 7 joules of energy for every kilogram that we burn. Okay? That's much less. In other words, nuclear energy, according to our calculation here, is about 200,000 times more efficient than fossil fuels. In the sense that if we burn a kilogram of fossil fuels, or if we let a kilogram of nuclear material undergo fission, we're going to get about 200,000 times more energy out of the nuclear fuel than the fossil fuel, okay? So I want to give you the basics as to how nuclear power works. So we know that when an atom undergoes nuclear fission and the nucleus splits into 2 or more smaller nuclei, that energy is released in the process. And if we have a whole bunch of atoms that are undergoing nuclear fission at the same time, that can actually generate a substantial amount of heat. Now, the idea is we can use the heat that's generated in nuclear fission to power a steam turbine. So this is what we call our reactor. This is where we keep the nuclear material, typically uranium, and the heat generated by that uranium as it undergoes nuclear fission is used to turn liquid water into steam. And that steam that's generated is then going to power a steam turbine, which is basically just a heat engine. We learned about heat engines back in chapter 20. So the steam generated by the heat is powering the turbine. It causes it to rotate, and that rotation is used to power a generator. So this is an AC generator. You may have seen one of these on a smaller scale if you've gone out camping to power, let's say, an RV. It works pretty much the same way on this large scale. The rotation generates AC power, and that is used to power our electrical grid. So this is what's going on inside of a nuclear power plant. So as we've seen, nuclear reactions can release a lot of energy. Now, if these reactions happen very slowly and in a controlled environment, we can actually harness that energy that's released to power our electrical grid. Now, the dark side of this is nuclear weapons. So nuclear weapons are designed to create a chain reaction of nuclear fission events or nuclear fusion events in some case. And that releases a large amount of energy in a very short amount of time. So it's not releasing that energy in a slow and controlled manner. It's just releasing that energy all at once. So to create a chain reaction, let's take a look at the diagram here to see what's happening during a chain reaction of nuclear fission events. So we'll start by sending a particle at a very high velocity towards a nucleus. This particle could be a neutron, for example. And it hits the nucleus so hard that it splits it and creates a fission event. So this nucleus gets split, undergoes fission. In the process, it's going to send off some particles of its own at a very high speed. So this neutron will hit another nucleus, cause it to split, and then cause it to send off a bunch of other neutrons. So those can now go off, hit another nucleus, which splits and sends off more neutrons. So you can see what's happening here is a chain reaction. This gets out of control very quickly, and a lot of energy gets released in a very short amount of time. So to give you a sense, the most powerful nuclear bombs that exist convert just a couple kilograms of mass into about 10 to the 17 joules worth of energy, all within a fraction of a second. And what we see is something like this, the characteristic mushroom cloud created by this nuclear blast. So that's how these work, okay? So we're going to end this video here. I'll see you in the next one where we'll wrap up this chapter and finish up our discussion of the theory of relativity. So I'll see you then. Until then, take care, be safe out there, be healthy. See you later.